Alright, so this is like a slight review. We kind of already hit on this with the fundamental theorem of calc. So, but it's like an important intro before we go into area between curves and volumes, just to go back and reiterate this because it's been so long. So essentially what we're doing is finding rates of change with net change applications. So before plus change equals. So yesterday, one of the questions on the mock exam we kind of discussed at the end was, okay, what do these two integrals mean? And one was the integral of velocity and one was the integral of the absolute value of velocity. So the key words between those two are displacement and distance. Displacement is change in position. So if I start on block A and I end up at block B, my displacement is my ending position. My movement or my distance may go from A backwards, then forwards to B. That's my distance. So it's 2 steps forward, 1 step back. My total distance is 3 steps. However, my displacement ends up being 1. So we have an integral that represents displacement. So the basic or general integral represents displacement. So yesterday on 3C, whatever that question was, the first integral you should have described as the integral from A to B of velocity to equal either position or displacement. And then we say in order to find a new location, your new position, which we'll call S of B, is equal to your initial position plus your displacement. And that should look a lot like the fundamental theorem of calc to you. So new position is equal to initial plus displacement. So we're going to hit on again, just kind of talk a little bit about the velocity, position, acceleration over the next day or so. Total distance is the absolute value. So again, in that same question, it had the absolute value from A to B of velocity. And what they were looking for you to tell them is that that was the total distance. So you can find the total distance by finding where you have sign changes so that you can get the area above and then subtract the areas below. Or get that absolute value of area. Right. So it says, suppose the velocity of a particle moving along the x-axis is given by, when is the particle moving to the left, when is the particle stopped, and when is the particle moving to the right. So, how do I know when a particle is going left, right, or stopped? This goes back to your days of thinking about your derivative and your sign chart that goes with it. So a particle is stopped when velocity is what? 0. So the first thing I want to do for this problem is to find when velocity is 0. Because when velocity is 0, the particle is stopped. So the particle stops at 1 second and at 2 seconds. if you were writing that out as a sentence or a justification, then your sentence or justification would be the particle is stopped when v of t equals 0, and in this problem at t equals 1 and t equals 2 seconds. So then to figure out if it's moving to the left or to the right, we have to look at the sign and determine if the sign is positive or negative. So we only actually care about 0 to 2. So I'm going to start my little sign graph at 0, and then I only need to go out to 2. So I need to know what's happening from 0 to 1 and what's happening from 1 to 2. So we're going to plug in 0.5 or 1/2. You can plug that value in to factored form because, again, all I care about is the sign. So 1/2 minus 2 is negative. 1/2 minus 1 is negative. A negative times a negative is positive. Therefore, this particle is moving to the right from 0 to 1. So the particle moves right from 0 to 1, not including 1, because at 1, the particle is stopped. Now, the 0 you can include or not include, it really doesn't matter. Because velocity is greater than 0, you could also write out, so you can write v of t is greater than 0 like that, or you can write v of t is positive. Checking for the next part, we plug in 1.5 or 3s. So 1.5 minus 2 is negative. 1.5 minus 1 is positive. Therefore, negative times a positive is negative. Therefore, and I'm running out of room, the particle is moving to the left from 1 to 2 because v of t is less than 0. That's like my short summary version. I can't fit any more on there. So why? Why is all that all of a sudden important to us again? Why do I care about the stop? Why do I care about the left? Why do I care about the right? Because now I want to actually evaluate that integral to find out what was my final position and what was my displacement. So like, did the particle run to the left and then did it run backwards and then did it end up in the same spot it started? Is it behind itself? Is it ahead of itself? So why do we need to know when it stops is because it tells me when it changes direction. So find the particle's displacement. So remember, displacement, think position or placement. Where is the particle placed? So distance is total movement. Displacement is where is it at. So it says displacement for the given time interval is s of 0 equals 3. What is the particle's final position? So our interval is from 0 to 2. So I want to know what is its final position. So I am looking for s of 2 given s of 0 plus the integral from 0 to 2, and to get final position, we integrate velocity, and I was given velocity up above. final equals initial plus change, or plus the integral of velocity. So S of 0 is 3. To integrate velocity, we're integrating 6t squared. So that's going to become 6t cubed over 3 minus 18t squared over 2 plus 12t evaluated from 2 to 0. What's really nice is evaluating at 0 is always 0 as long as there's a variable involved. So I get 3 plus, and what I want you to notice too is, what am I doing? I'm stacking my equal signs, or in your case, you could draw arrows or keep writing the equals, but one of the things I've noticed is that we're bad at fluidity. We need to make sure we show step 1, step 2, step 3, and we need to make sure that somebody else can follow that train of thought. Because if the AP reader can't follow your train of thought, you're kaput. I know how you think because I know you by now. They are just looking at a glimpse of it. Okay? So we have 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 minus 0. 2 cubed is 8, 8 times 2 is 16. 2 cubed is 2 squared is 4, 4 times 9 is 36. And 2 times 12 is 24. So 24 and 16 gives me 40. 40 minus 36 is 4. 4 plus 3 is 7. So the particle's final position, or its position at 2 seconds, is 7. So again, that's where the particle ended up, not how many steps or points it took. So then this one says find the total distance. So total distance is absolute value of velocity. So if I wanted to find the total distance, you're talking about 0 to 2 of absolute value of velocity. But the only way to get absolute value of velocity is to know where the particle changes direction. So in order to get velocity as an absolute value, if the particle is moving to the right, which it was doing from 0 to 1, we add it. The particle is moving to the left, which is representative of backwards. We're going to subtract. So we're going to add the integral of velocity from 0 to 1. And then to make that left or movement backwards, we're going to subtract the integral from 1 to 2. So remember that the integral from velocity of 0 to 1 is kind of like saying s of 1 minus s of 0 minus s of 2 minus s of 1. That's top minus bottom, and antiderivative of velocity is position. So we just calculated s of 2. We said s of 2 was 7. We were given s of 0. S of 0 is 3. So the only one I don't know is s of 1. So again, I could take my antiderivative of velocity So S of t is equal to 2t cubed minus 9t squared plus 12t. And then I can plug it in. Yes, this one's good. Oh, good. I'm curious if I did it without plugging in all the numbers right now. I think it's like we didn't have a plus 3, so I'm not sure. I might do it the long way. So its total distance traveled is 6 meters. And again, that should kind of make sense that if its total distance traveled is 6 meters and it ends up at 7 and you started at 3, it's kind of like, oh, well, it went 4 forward and then 2 backwards and there's your 6 and that's how you get to 7. We can also talk about these with graphs. I actually think graphs are easier than equations because the graphs already tell you the areas of each individual segment. So here we're given that the particle moves from 0 to A. So if the area under the curve is 10, then that's like saying the particle goes right 10 units. If the area under the curve from A to B is 9, but it's below, then it goes left 9 units, and then it goes above again. So it says, what is the particle's displacement from 0 to C? So remember that displacement is initial and final plus change. So displacement x of C equals x of 0 plus the integral from 0 to C of v of t. Well, v of f in this case. So x of 0 is 10 plus 10 minus 9 plus 8. So it's initial plus all the areas under the curve where the signs are their actual signs. So 10 plus 10 is 20, 20 minus 9 is 11, 11 plus 8 is 19. What is the total distance traveled by the particle in the same period? So now its distance is all of those sums positive. So it's 10 forward, 9 backwards, but that's really like 9 steps, 8 forward. So the particle moved 27 units. give the positions of the particle at A, B, and C. So x of C, which is this, kind of comes down here. And then A is 20. Now for B, you can pick it back up at A and do A plus B, or you have to do all the way at 0 and do A and B again. So I could technically do 20 minus 9 to get 11. Going backwards in time and then incorporating derivatives with this problem. It says, where does the particle achieve its greatest negative acceleration? So a particle will achieve its greatest negative acceleration when the slope of velocity is the steepest and going down. Because if you want a negative acceleration, velocity needs to be very, very steep and going down. You're only considering to point B. So if you consider this point over here, then it's definitely at C. But this one says on closed interval 0 to B. So that's part of the trick too. They want you to say C, but like C isn't in the interval from 0 to B. So in that case, I'm looking at these. Probably the steepest. And then where does it achieve its greatest positive? Well, that's going to be where it's the steepest. So I would say just after. And since we don't have numbers, just after. Makes sense? But that, again, that's like going backwards sort of towards derivative knowledge. You know, it's something. It's on tomorrow's notes. Yes, I also like accidentally inserted tomorrow's notes. The graph of velocity of a particle on the x-axis is given. The particle starts at x equals 2 when time is 0. Find where the particle is at the end of its trip. Find the total distance traveled by the particle. So the particle graph is going to have a velocity. My graph is like Alright, velocity is not only rate in which you can integrate to your total. In fact, if you were given a function that gave the total number of tickets per hour that police officers wrote each day, you'd be able to find the total number of tickets in a 24-hour period. So speaking of all these beaches that we've been talking about today, certain beaches have to add or remove sand depending on the tides. So we'll call our beach Sandy Point Beach at a rate model given by R of T equals a pumping station adds sand to the beach. So again, we've talked about rates of change before. We have rates in and rates out. This goes back to that same idea. So we have R, which is going to be the rate at which it is being pumped in, or being removed, sorry. S is the rate at which it is being pumped in. So R removed, S is added. So both of them are in cubic yards, which means these are volume equations. If we are only comparing it for 6 hours, and at the initial time there was 2,500 cubic yards, where are we at now? So how much sand will the tide remove from the beach during the 6-hour time period? So I only want to know how much is removed. I don't care about the initial. I don't care about the adding. All we are looking for is how much is removed. So if my equation R of T represents the tide removing sand, what I integrate or derive to find the tide, how much sand is tide removed. What is the out? What did you start to do? Something. Alright. So think about R of T and its units. So if you integrate that, what would your units end up becoming versus if you derive it? So how do our units work, right? And even if you go back to your good old days, if S of T is meters, then its derivative became So if I have cubic yards per hour, what am I trying to get rid of? The hour, right? So if you want to get rid of the hour, you are going to go from meters per second to meters. So we're going to integrate. And I think that's why it's nice to see the position one, because you understand this. So if you get stuck or you get confused, you can always use that as a reference point. So we're going to integrate from 0 to 6 of R of T. You're going to do that right on your graphing calculator. I'm going to do any of this by hand. You're going to put that in Y1. You're going to put S in Y2. You're going to hit 0 to 6. Integral R of T dt. What'd you get? Oh, that seems good. 31. You guys are in grades, not crazy. 2 plus 5 sine 0.16 pi t. Oh no, I was reading it to college. 31.8. Got it. that would be cubic yards. So it said indicate units of measure. Write an expression y of t that would represent the total number of cubic yards on the sand at time t. So y of t is kind of going to be like my displacement formula, right? It represents the number of cubic yards of sand at any given time. So I know that at y of t equals 0, I need it to be 2,500 because that was the initial amount there. So it's going to be 2,500. Is R adding or subtracting sand from the beach? Yep. So we're subtracting the integral from 0 to t of R of t dt. And we're adding the integral of 0 to t of s of t dt. So it seems backwards because I feel like oftentimes we get the rate in and then the rate out, but this problem started with the rate of removal. And you could flip the order of s and r on your paper as well. You don't have to put the subtracting first. You could add, then subtract. Find a rate at which the total number of yards is changing at time t equals 4. So all you're going to do is everywhere you add a t on your calculator, you're going to go back in time and change all those t's to a 4. And I just saw my calculator for what we get. Agree? Disagree? Thumbs up? Okay, what would my units be? Okay, so let's just go with yards because we integrated. So does that matter because it's the same kind of rate? So that represents the yards of sand on my beach, right? So if you wanted to find the rate at which the total amount of sand on the beach is changing, how could I get that unit to have time? Derive. So on your calculators, this would be that FTC problem where you took like the derivative of the integral. So remember when we did like d dx from 0 to x, da 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 da. So or if you had just plugged in to the originals, you would get your rates. Because the originals represented it's just important because I feel like they like set you up to do that. And then I want you to make sure when you look at your units, you see, oh, it gave me yards. Because I feel like AP does that a lot. And that's like something that sometimes I feel like I need to convert to boop-a-doop-a-doop. So instead of actually plugging into this formula that represented total number of cubic yards, you would actually just want to plug into our originals. So our originals would just have been, and you can go to your table, you can also just go, I don't know if I know how to do it the way I want to. It would have just been S of 4 minus R of 4. So it's what you're adding and what you're removing. And that will give you yards cubed per hour. But I don't think there's like an easy way to do it. You could go to Y3 and you could do Y1 minus or Y2 minus Y1 and then go to your table and plug in 4. But it's probably easier just to like plug in figures. What do we look again? What? Agree, disagree, so we can pull up my answer. Correct. Yeah, that's all I have. On my calculator. And then I try to show, like, remember I said it's the fundamental theorem of calc where you derive the integral to get the rate. So it's like dy dt equals y prime of 4 because it's said rate. The last one, if you look at that, any guesses on what we need to do for the last one? It's very similar to other ones we did in the past. Yes. So in this case, you would set, well, kind of the derivative. So it'd be the derivative of y equals 0. So like that. Which is actually going to end up giving you r of t has to equal s of t. So if you think about it, you want to know when could something be a minimum? Well, something is a minimum when the derivative is equal to 0. So if y of t represents my original function, if I want it to be minimized, you derive. So the derivative of that would be y prime of t. So the derivative of 2500 is 0, gone. The derivative of the integral of r of t is negative r of t. And then the derivative of the integral of s of t would be positive s of t. And then to get a min or a max, your derivative has to be equal to 0. So then I need essentially r of t to equal s of t. And everywhere r of t equals s of t is a potential minimum, as well as where we started and where we ended up. So you started at 0, 2500. I get that r of t equals s of t at 5.117.
And we get that by
Second trace intersect, yep, on your graph. So then I need to know y 0. I need to know y of 5.117. And then I need to know y of 6. And then it says on what type t is the amount of sand on the beach a min, what is the min value, and then justify. So my minimum is at y of 5.117 because there's 2,492.37 cubic yards of sand, which is smaller than both 2,500 and 2,493.28. Does that make sense? Almost right. They're 12 through 16 are all about the same graph. They're like that ABC problem we did earlier today. We haven't done them for a while. Let's do some true false messages. That's it. Alright, tomorrow we'll do one last part to this.